All right, hello everybody. Glad to be here, and I appreciate the invite to come and talk about technology. I think is really cool. We're talking about DIDCOM today. If you don't know what that is, that's fine. We'll walk you through and kind of explain some stuff. You're welcome to ask questions at any time. I may not get to them right away, but I will. But you're welcome to ask while it's on the mind, and then I'd love to be able to fill in any details or answer any questions. I am Sam Curran. I work for Indicio. We're a company that provides commercial solutions based on open source projects. We're heavily integrated with all the open source communities and contribute heavily to them. I'm the co-chair of two relevant working groups. One is the Hyperledger Aries working group. Aries has been working on software for SSI and decentralized identity for years and years. And so I'm heavily involved there, and I'm a co-chair of the DIDCOM working group at the DIF, which makes me, I think, approximately qualified to present on it. I'm Telegram Sam on all the socials, and you're welcome to contact me anywhere about that, and reach out, and I'd be happy to talk. That would be great. So what is DIDCOM? It's secure private peer-to-peer messaging. And a good comparison here is to think about verifiable credentials are, of course, a popular topic. Verifiable credentials contain information about the subject, about the person, and DIDCOM is about communication with the subject. And so, of course, they get along really well, but hopefully that is a little bit of a foundational step to help you understand what it does and why it's useful, rather than the signing of data or anything in that particular thing. It's designed to enable communication between any two parties that have DIDs, and that it's called DIDCOM. So hopefully we nailed the name association with the technologies underneath it. But that's what it enables. It's about communicating. You can communicate about lots of things, including verifiable credentials, but it's fundamentally about communicating. So here's a flow. If we have Alice up here in the corner, Alice can compose a message and then encrypt that message to the recipient. In this case, I'm gonna call this person down here Bob, and Bob can then decrypt and understand the message that is being sent. There's a lot of vagueness in the arrows here, kind of our purpose. I'll get into some details about transport and some other things in a minute, but this is the basic idea. DIDCOM itself is asynchronous, and it's message based. I'll get to that in a second. But it also is one directional in the sense that you form bidirectional communication simply by both parties actually just sending messages to the other party in kind of a reverse manner. There's a little bit of a not quite symmetrical in this server here, and DIDCOM allows for untrusted mediators to be used to relay messages in a way that allows for untrusted or that allows for the human devices to be first-class participants in the protocol. So what I mean by that is that if you have a protocol or a system that is API based, then you're required to host that API on at least a system that's mostly available. DIDCOM, through the use of mediators, allows for messages to be received by an untrusted online service, but then relay it to a device when it comes online or comes into signal. So devices like phones and laptops and IoT devices and things like that work really well with this because they're not always on and they're not always highly available. And so the goal of this design was to allow the devices that humans use the most to be full participants in the protocol. It is a peer protocol in the sense that all of the participants from a protocol perspective exist on equal ground. In lots of architectures, it's very client-server. There's definitely a client and there's definitely a server, and they have different roles. And in the architectural differences of those things are not the same with DIDCOM because of this design that allows for both asynchronous messaging, but also the use of untrusted message mediators or message relays in order to support the types of devices that humans use the most. The encryption used is authenticated encryption, which means that in the process of decrypting the message, you gain cryptographic confidence of the sender of the message, which means that that there isn't, you're not going to see signing in my description here, and you can sign to give you non-repudiation if desirable, but the actual basic encryption provides the cryptographic assurance of the sender. So JC asks, is there complications with security when incorporating IoT? The biggest complication with security with IoT is the types of keys that are supported on hardware devices that are often used by IoT. So there's when you say IoT, there's quite a spectrum of capability. You have all the way something that's like a pure little microcontroller, think like an ESP32. It can kind of go all the way up to the point where you have something with like an embedded Raspberry Pi in it. And so there's different kind of capabilities there, and it's a little difficult without speaking very specifically. But the goal is that there are no security compromises there with the involvement of the protocol. It does involve stuff that is not necessarily designed for very low byte transmissions. So stuff like LoRa doesn't work quite as well without some sort of a bridge or a translation into the full DIDComm protocol. So we're not reaching that far down into the IoT stack. So hopefully that was helpful, JC. So what kind of properties do we get from DIDComm? Well, there's lots of really obvious ones that we want. We want it to be secure and private, et cetera. Interoperability is pretty great. Transport agnostic is actually a really pretty important one. It uses transports. I'll talk about some of those, but it doesn't derive the security properties of the protocol from the transport itself. For example, HTTPS has some encryption on the transport, but that's not the types of things relied on by DIDComm, because in the transmission of a message, we want it to work with the same trust properties across Bluetooth as it does HTTP or WebSockets, and you don't have to care. For example, if it passes through a mediator and the transport changes, you don't want to have to care about the properties being derived from the transport itself. It's also extensible, which is pretty important. And I'll get to a comparison with HTTP APIs in a second, but similarly, you can develop your own protocols to ride on top of DIDComm. So DIDComm, in a way, is a meta protocol that allows for you to then extend the protocol with the definition of different message types and data that you'll be transmitting back and forth between parties. And that enables you to do some really cool stuff, including like without permission. If you just want to do something, you can just do it. You don't have to get approval from anyone to be able to pull that off. And I'll talk a little bit about that more as well. Here's some of my favorite properties of DIDComm. I mentioned it's message oriented, and this is very deliberate. And so the protocols inside of DIDComm are sets of messages with an explanation of who sends what message and why, et cetera. And so that's an important aspect of it. Because it's message oriented, it can be asynchronous. This is super helpful, of course, when you're trying to communicate with a mobile device that may be in a tunnel or have a dead battery. And so the ability to carry out these types of interactions in an asynchronous manner is important. In my demo that I'll show a little bit later today, that a coworker and I hacked together, you'll see that asynchronous doesn't necessarily mean slow. Because of the technologies involved, we understand the importance of good user experience, which means that the user doesn't necessarily know it's asynchronous when, of course, they're connected and they have battery and things like that. But you still have those benefits. It's also routable, and this is the mediation that I spoke of that allows you to bypass sort of typical network connectivity issues. So we've talked about mobile phones and things like laptops, but that can also be devices that happen to exist inside of behind a firewall, for example. And there are easy ways to handle the fact that you're behind a firewall, but still be able to communicate and interact with the outside world in pretty powerful ways. So this is a message-oriented protocol. What does a message actually look like? Here's an example from a protocol called Basic Message. It's exactly what it sounds. It's a basic protocol that allows you to send human-oriented messages to another party. There's a couple of interesting things that I want to point out about the message. The ID here uniquely identifies the the message unique to the sender, so that you can keep track of different messages, or message redelivery. If a message is partially delivered or the delivery isn't sure, sometimes the delivery will be reattempted, and that allows you to handle that. The message type indicates what types of content you're actually expecting in this message. And so message types are URIs, and there's a couple of different components here. Up until this slash right here is the name of the message itself. So this is based on the documentation and where it's hosted, but this would be didcom.org, which is a community resource for hosting protocols. And basic messages is the message family of this protocol. Then we use major minor semver for the protocol. So if there's rules about what needs a minor version versus a major version. Basically, newly added optional things can be handled with a minor, but a major is required if the semantic meaning of anything changes or anything is removed. And then finally, this is the name of the message within the protocol family itself. This protocol is really simple, which is why it makes a good example. There's actually only one message type, and that's message. The lang indicator here specifies the language of the content here, so that if you're using language translation, you don't have to guess. You know the source language it is, and you can use software to translate it into another language. The timestamp that it was sent, and then everything in the body is actually specified. That's where all of the attributes, message attributes unique to the message here, are actually placed. And so the actual content here is the message that's unique to the protocol message itself. So that's a simple example of what this looks like. This is called DIDCOM, and before you actually get to the point where you're sending a message, you have to have a DID, of course, that's capable of supporting service endpoints. So this is a service endpoint from within a DID document that is DIDCOM capable. And I'm going to point out two things that are the most important here. One is the URI, and this is the endpoint where messages can be transmitted when you're trying to send a message to the owner of this DID. The second thing is routing keys. There can be 0 or more routing keys that specify the use of mediators. And when you use a mediator, then you encrypt. You take the message, wrap it in a forward message, and then encrypt that to the mediator itself, which accomplishes some important privacy features of message hiding for anyone that happens to be inspecting network traffic along the way. So any DID of any DID method that's capable of having a service endpoint that describes a DIDCOM messaging endpoint, as shown here, can be used with DIDCOM. It doesn't beyond this. It doesn't care about the properties of the DID method or what's using, or what it's built upon. So this is a diagram that we use to kind of help people understand where this fits into the world. The DID resolution is the process, of course, of taking the DID that you have, the decentralized identifier, and resolving the DID document from it. Out of the DID document, you have both keys and service endpoints. DIDCOM uses those. And DIDCOM also travels across different transports, but the transports itself are not necessarily specific. For example, HTTPS or WebSockets are transports that are used in other places. And it uses those to actually move the message, but not derive the security properties, as I mentioned. And then on top of DIDCOM, you have the creation of a variety of protocols that then leverage sort of the batteries included nature of DIDCOM in order to communicate things with different parties. So basic message is the protocol that we looked at the example of. But there's also issue credential and present proof and a handful of other protocols, both verifiable credential related and not. And so the dots here clearly indicate that nearly anything can be built upon DIDCOM in order to make those things happen. So a likely comparison to DIDCOM in the interaction of several parties across the internet is with HTTP-based APIs, which are, of course, very common today for good reason. It's a good way for systems to talk to each other across the internet. And so here's a little bit of comparison, and I'm not going to mention everything. But there's a handful of things that are very similar in the sense that you tend to use paths within an HTTP API to designate sort of which handler is going to be processing any particular post or get request or whatever type of request. In DIDComm, it's similar. You use the path of the protocol itself in order to route messages to handlers in that way. There's HTTP APIs are typically one request, one response. And so that's kind of how, the client reaches out to the server and comes back, and that's it. Things like webhooks are kind of doing that in reverse, but the webhook still has a client and server. They just trade roles. DIDComm is defined in such a way that there's no expectation that there's a one message to one response as it happens. It's okay if that happens in protocols, but there's no expectations. For example, with an IoT device, you might have an IoT device that sends routine messages of what a temperature is or the amount of light that the sensor is picking up, without ever really getting or expecting a message in response according to the protocols it implements. And so there's all sorts of scenarios that are possible with DIDComm because of the lack of expectation that there's a one request, one response interaction model between the two. Where's the message stored? Is it broadcasted live without storage in DIDComm? DIDComm is a transmission protocol. So the messages are only stored with of course, with the originator of the message and with the recipient of the message. And if the recipient has arranged for a mediator, the mediator can temporarily store that message prior to it getting to the ultimate message recipient. And so if I transmit it to a mediator and you are online, it is typically immediately delivered to the other party. And then they can do with it whatever they want. They can store it for a long time. They can read the message and process it. The actual processing of DIDComm messages is more specific to the individual protocols than DIDComm necessarily. This is all about how to get a message from one party to another party. And storage is actually not a part of it. So Reddy, you asked, do we need additional permission to delete? This is not an this is of course is comparing HTTP APIs. DIDComm itself has no concept of deleting itself. A protocol built on DIDComm can have the concept of deleting, but DIDComm itself as a foundational protocol doesn't have the concept of deletion, as it's only a message transmission protocol. This comparison with HTTP APIs and DIDComm is important. This is because it solves a silo problem that's also really powerful. This diagram here, credit goes to Daniel Hardman for creating this slide. You'll notice that my slides are not amazing, and this looks better than most, and so I need to provide proper credit here. When you build an HTTP API, it fits the server that it was designed for, and there are methods to handle these sorts of features that you need. But it would be ridiculous to assume that I can design a protocol that interacts with that's designed to talk to Twitter's API, for example, turn around and use that exact same API and the exact same client that I've built to talk to Facebook or to any of the other properties online, because those APIs are different. You have to design the client for the specific API. There may be some common things with authent mechanics. For example, OpenID is a really common way. The OpenID protocols are a common way to do resource access for that. But most of the API is very, very similar, which is why we have tools like Swagger that have been developed to make it easier to develop clients, because you have to develop a client per each API that you call. The peer-to-peer nature and the protocol design of DIDComm provides a different experience, where a peer that implements a protocol on top of DIDComm can speak that protocol with all of the other peers that speak that protocol, even though there may be some other features or other things that they support. So if I support 6 different protocols, and I can speak any of those with other peers where I share that compatibility of that. We do have discovery is a built-in feature of DIDComm, where you can ask the other party what they actually support. So you can query the other party and say, hey, what protocols do you support? Or you can ask them a specific question, do you support protocol X? And that way you can discover that automatically between different parties. That's particularly useful when there are several protocols that do approximately the same thing, or they're in the same space, perhaps different versions of a protocol, and you need to know which version of the protocol or which similar protocol to talk with the other party. And so discovery helps with that process. The nature of this is that you can end up with common types of interactions with a lot of other parties that are online, as opposed to having to develop an API specifically for this. Here's an example. Let's say there was a business hours protocol that let you ask a business what hours that they were open on a particular day. That protocol can be supported by a variety of businesses. For example, a pizza place could implement that, but also like a loan escrow office could. And because that protocol is supported by both of them, I can ask both of them the same question and get an answer back about what their hours are. Now, the rest of the protocol is likely supported by a pizza restaurant, which could include placing an order. Wouldn't really apply to an escrow company, and an escrow company would have APIs, for example, around making appointments or signing documents that are unlikely to be supported by a pizza company. But the ability to support the common pieces or the common protocols is a very powerful thing that we don't have on the internet today with how we design our interactions. And DIDComm provides that in a really useful method. So we keep talking about protocol. What is one? Here's the components of a protocol. We've talked about the unique URI that you use to keep track of the protocol itself. Also, the messages within it. The protocols also have defined roles and state and sequencing rules. The messages that are actually part of it in the form of events that they can send, and also constraints on the operation of the protocol. And those are defined unique to the protocol because they vary quite a bit across different protocols and the needs that they have. So here's the basic message protocol that we saw the example of first. It has a name and a version. It's the 1.0 of basic message. And here's the type name. And there's only one message definition for the message type within the basic message protocol. There's a sender and a receiver. It's a very simple state machine here because of the simple nature of the protocol. And you send a message and the other party receives it. And there's no particular trust or incentives involved in that protocol, and so there's no definition there. And we'll look at some types of the other protocols, and I can point you to resources where you can discover other types of protocols that exist for this. And so there's lots of different things. So the docs link, so didcomm.org, if you go there and you can navigate or search, is probably the best place to find the documentation for the various protocols. If you want to browse around while I'm presenting here, that'll be the quickest way to make that happen. Oh, thanks, Angela. Appreciate that. So we've talked a lot about what messages look like in their unencrypted state, but I want to talk about the security that you gain from making this happen. So here's just a sort of a made-up example protocol here with the from and the to added, as well as the timestamps that are involved. And then, of course, the body, here's some attributes that are involved. The contents of the message are uninteresting for this bit where we talk about encryption. The process of encrypting a message to the recipient, we tend to call it packing the message. And it involves, of course, the message itself and the recipient's public key and your private key is the encryption. It's not simply encrypted to them, but it's encrypted to them from you because of the encryption that we're using. So an encrypted message, actually a packed message, actually looks like this. You'll notice that this looks a heck of a lot like a JWE because it is. And so there's protected attributes that you can process. There's initialization values and tags involved, and also the ciphertext of the message itself. And so here's the different contents of the previous slide, and the message itself is encrypted into the ciphertext. The rest of these values relate to the encryption itself. If you go inspect the actual encrypted stuff, then you see the information here, and the message itself, which looks a little something like this, ends up in the ciphertext as part of that. And so that's part of it. You don't libraries that implement this, that implement DIDComm, typically do this for you. Walking through the encryption is something that no one really wants to write, and everyone's freaked out about getting wrong. And so the use of encryption libraries, of course, is heavily encouraged that already do the encryption. And if you've got a DIDComm library that provides you the support all the way through, that's even better because you don't have to even worry about how to call the encryption library. The I talked about transports a little bit. The three most common are HTTPS for obvious reasons, and WebSockets as well as Bluetooth. Bluetooth is really cool because of course you can transfer it directly between two devices, two phones or something else, and end up with the same security properties. And you don't have to use the same transport to talk to the same other party all the time. So if there's someone that you normally communicate with using HTTPS, and your phone is capable of discovering that they're nearby and support DIDComm over Bluetooth, then you can begin exchanging messages directly with the other party in that manner with no change in security properties, which is pretty cool. WebSockets is incredibly useful when mediators are in use, and the demo that I'll show later can highlight how important that is. It can provide for really rapid delivery of messages in that particular case. WebSockets are really good when there's a high volume of messages traveling between two parties, just because you don't have to set up and tear down the connection, but you can just transmit it over the WebSocket like that. So there's lots of different types of protocols that are supported on top of DIDComm. Here are 4 that relate to verifiable credentials. So there's an out-of-band invitation protocol that facilitates introducing two parties to each other. And so that's really helpful. This often shows up in the form of a link that is emailed to someone or a QR code that someone can scan that helps sort of bootstrap the relationship. There are other ways of doing this, of course. DIDComm only requires that you know the DID of the other party. So if that can be discovered in any other manner, and there's several methods of doing that off of websites or other things like that, then that also works. Out-of-band invitations can also facilitate interactions. So if the purpose of the user connecting to you is to have a credential issued to them or to present a proof to you, then you can include hints in the out-of-band messages that can automate or streamline that process for the user. And then, of course, issuing credential and presenting a proof. These are great protocols that are agnostic to the actual format of the credential itself. And so any credential type can be passed alongside those protocols. And then when revocation is used, there's a revocation notification protocol that can be sent to notify the holder that the credential they have has been revoked. This is an important one because lots of these other ones involve the user being more directly involved, like they're staring at a website or they're in person, interacting with another person directly. Revocation typically happens when the issuer and the holder of a credential are not next to each other or not in the vicinity or not engaged in an interaction. And so this DIDComm and the architectural nature of DIDComm allows for the issuer to send a message to the holder saying, hey, by the way, I've revoked your credential. And that works even if you are not even if you're not engaged in an interaction. The user can receive that on their phone. Their software can help them process that or know what to do with that. For example, know that they can't present it anymore or go to get a credential reissued that is correct in the case that's been removed from there. But aside from VC protocols, the other collection of protocols that's become really popular are protocols that are designed to handle human communication. So basic message is one of them. There's also a question and answer protocol and an action menu protocol that can help you with that. So Simon, the link that you have right there to DIDComm messaging is the spec repo for the DIDComm spec. And there is, I'll get to libraries in just a second that can kind of help you understand what libraries are available and where to find those links. So human communication protocols and verifiable credential protocols actually work really pretty well together in the sense that often you need to communicate in human terms about what's actually going on with the verifiable credentials. And so the mixing of these protocols together, the way DIDComm allows, can allow for a message from someone to another party saying, hey, the reason I'm asking you, I need to ask you for a credential for a specific purpose, and I want to explain why. That can happen in using a basic message and then engage in the credential exchange protocol, which provides some really useful, human context for the person that is asking to be asking to present a credential. Of course, there's lots of other different types of protocols that can be developed on top of DIDComm, but these seem to be really popular with the types of interactions that people want to create for the necessary user experiences. I spoke of out-of-band invitations. This allows for the DID and optional metadata to be passed in something like a QR code or a link between parties. And that contains all the necessary things to make the connection actually happen. this is kind of not as cool as the previous diagram, but the idea that as soon as Bob knows Alice's DID, then Bob is capable of constructing it, encrypting it to Alice, and then transmitting it possibly through a mediator if Alice desires in order to get it to the other party. So I'm getting along in the slides here. I don't have too many left. One of the things that I did want to highlight is that if you're Googling around, there is a previous version of DIDComm that was born within the Hyperledger Aries community. And there is active production use across vendors and code bases. It is more loosely based on the JWU standard. DIDComm v2, which is what everything I've been talking about today, has made some important changes that make it a little bit easier to use. And so it's better, it's simpler, it's a little bit more flexible in the ways that matter. And so I just wanted to highlight that there are in fact 2 versions going on. So DIDComm v2 is all the stuff that I'm talking about today. I just wanted to highlight that that version 1 did exist. And if you happen to find something that seems like it doesn't quite line up or doesn't look the same, you're probably looking at something related to DIDComm v1. So now libraries, and I'll show you where these are actually like linked on my slide, which is not super useful to you because you don't have the slides yet. But I'll show you in a second where you can actually go find these links directly. That way you don't have to. You can just follow the links. And so here's some libraries. I have DIDComm libraries listed along PeerDID libraries. You don't have to use PeerDIDs with Python or with DIDComm, but it's really common. And so I wanted to kind of include those libraries just to be useful. And there's good links in a various number of platforms here, as well as a Rust implementation that gets you WASM support, etc. And the demo that I'll be showing in a little bit is actually the WASM TypeScript version of a DIDComm library that we've got running in a browser. And so you don't have to type all these things. There's 2 resources for you. DIDComm.org is the community collection of DIDComm protocols that can help you out with that and find the documentation. The DIDComm book is another one. This is book.didcomm.org. Will actually point you to where the libraries are themselves. And so that's an important thing. And I'll show you in a second when I switch my screen sharing for the demo. I'll go ahead and show you DIDComm, the DIDComm book. This is inspired after the Rust book, and it's a growing resource. It does not have nearly as much as I want it to yet, but it has a growing collection of links and explanations that can be useful to you. The community is also pretty great. We are on. There's a user group on Discord that you can join to ask questions or be involved in the community if you would like. And yeah, so here is my last sort of slide, but I don't normally have a demo, and I'm going to add a demo today. So here's some links. You can screenshot this if you like to get there to the various places. And the Decentralized Identity Foundation hosts the DIDComm working group and user group. If you're a small organization, there's less than 1,000. I think I did the thing wrong, but if you're less than 1,000 people in your organization, then it's free to join the DIF, and you can get involved in any things that they have going on. We have user group and working group calls at Mondays at noon US Pacific, and there's details that you can find from the other links here if you're interested in joining those calls. Any questions before I jump to the demo and I hop away from my slides? If using blockchain for DIDComm, would only the DIDs be stored on chain? So yes, with a tiny bit of an asterisk. For DIDComm itself, only the DIDs are useful. So the DIDs and of course the DID documents that the information provide would be the keys in the service endpoint inside of the DID document. That's the only thing that the DIDComm cares about. If you're using a non-blockchain based DID method, PeerDIDs or anything else, as long as it supports the service endpoint and can be resolved by both sides, then it's perfect in use. What are common ways in practice to initiate a DIDComm exchange? What would the user experience be like? The most common one is to prepare an out-of-band invitation that facilitates some sort of interaction with the other user. That ends up in a QR code displayed on a website and scanned by a user. And so that's kind of the most common sort of initiate experience. And then from the mobile phone perspective, you open it up to an app that understands the stuff. You scan the QR code, and then all the other interactions happen within the app. I don't have a demo of a mobile app today, but there's a number of them out there that do support that. Is it common to use relays to intermediaries to facilitate the initial discovery? This is going to become more common, I believe. There's been discussions about directories or other sorts of things, so that you could basically find the DID of the other party in order to begin that experience. So let's say, for example, we're involved in a hackathon, right? And it would be possible for the hackathon to host a directory that allows for people to submit a DID in there for discovery by other participants in the directory. So you could like Sam Curran, you could find me in the directory, find the DID that I've placed there, and then use that to initiate a connection and communicate with me. I think that's going to be more common in the future. It hasn't quite yet been, mostly because the initial use cases actually in all of decentralized identity happens to be verifiable credentials instead of sort of contact discovery. But I think that will be something that happens and grows in popularity relatively soon. Do most wallets support DIDComm interfaces? Depends on the wallet. There's a set that are used within the community that is DIDComm friendly, that do support it really well with cross compatibility and interoperability. It depends. Most crypto wallets haven't really caught on to this sort of a thing yet, either verifiable credentials or that. But this can also be used alongside other protocols without really a problem. And so particularly anytime you have a DID that would be useful. Right now there's a whole bunch of hubbub about the OpenID for VC protocols for credential exchange. Those credentials do credential exchange, and they use the common OpenID patterns to do so. They don't support anything outside of credential exchange itself. So if you want to have other types of interactions, or you want to have credential interactions that fall outside of the interaction modes they support, then DIDComm's a great thing to add to that. Which ones can we use if we're building with this in the hackathon? This is something that this is a question I should have anticipated for the hackathon. There's a number of wallets in the community. There's out of Europe, some wallets that have supported DIDComm are the eStatus wallet or the Lissi wallet. There's one called Holder Plus that's produced by Indicio, based off of the Bifold code base. Bifold is one of the Aries projects related to this. And so I apologize for not having links ready to go, but I can pass them along to Angela for distribution after that. Yeah. Okay. Let me drop to a demo because I think this will be helpful for understanding. Okay, 9:43. Share. You get to see my whole screen because the platform doesn't have the ability to share multiple windows at the same time. And so, okay, so I have two windows here. This is not yet a publicly hosted demo, but will be shortly. This is code that runs entirely in the browser.
Oh, Sam, I think it's, at least for me, it's a bit small on the screen. Is there any chance you could make the Alice and Bob windows bigger or zoomed in?
Well, maybe. Let's see what happens here when I do this. That's a little bit better. We do the same thing over here.
Mm-hmm.
How's that? That was weird. Okay, hopefully that is a little bit easier.
Yeah, that's much better. Thank you.
Okay, so let me explain what's going on here. There is code in the page that's running entirely on the page. All the cryptography is happening on the page. This is all in TypeScript, and a bunch of stuff happened when I loaded the page. If I go ahead and click refresh on this, it'll actually redo that work. What it does is that every time you load the page, it will automatically generate a peer DID. A peer did is one that's not recorded on a ledger, but designed to be shared directly with the other party. This happens to be using did peer 2 for expedience in the hacking together of this demo. The peer did spec is adding a peer did 4, which has some advantages to it, but that's a bit of an aside. So these two tabs are not talking to each other with anything that is related specifically to this computer. So if this was a publicly hosted demo, you could pull this up on your computer, and the same things would work. There's a list of messages here that I'll get to in a minute to explain what happened. But the first thing that I want to do is kind of, and this is totally a developer-oriented demo, of course. I'm going to make a new contact here, and I'm gonna help them have each other's did. So I'm going to copy Bob's did, and I'm going to give it to Alice, and I'm going to call it Bob, and I'm going to create a new contact here, and I'm going to do the same thing for Alice. I'm going to take Alice's did and give it to Bob. In reality, this generally only happens one way, in the sense that like Alice gets Bob's did and then just sends Bob a message, and that's how Bob discovers Alice's did. In the case for the demo, we didn't get quite that far in our hack sessions over the last couple of days, including to like 2 o'clock in the morning last night, because we were kind of excited about getting the demo ready. So now Alice knows about Bob and Bob knows about Alice, and what they know about the other party is in fact the did. And they've resolved the did document to have both the keys and the service endpoints inside. So now if I click into in my interface into the connection that they have, I can send a message. Now you're going to see a couple of glitches possibly because of this, but you'll see that I sent a message from Alice and it arrived to Bob. That's a little less impressive unless you understand what's actually happening here, and I'll get into that in a second. But of course, so Alice and Bob are talking about tacos. The duplicated display of this message is not actually sending to, but it's actually just displaying to is one of the glitches that we didn't iron out in our hack session last night. But we did get the rest of it working, so kindly ignore the duplicate message there. So they're talking back and forth. Well, this is really unexciting. What's really going on here? So in this little scroll window, it actually shows the messages that Alice is using to communicate. And so if I scroll up here just a little, you're going to see that there's a DIDCOM message right here. Here's the content that says totally. This is a basic message 2.0 message. And there's a message ID here. And then you're going to see the from and the to. These are absurdly long because they're peer did 2 dids. Peer did 4 allows for a collapsed view after initial connection, which makes the did in use substantially smaller. But it's going from this did and then to this did as the other party, and then and that's what looks enormous. But there's a message flowing back and forth between the two. Okay, Sam, you say, if there's no actual browser tab to browser tab communication going on here, how does the message get from this window to this window? What we have to make the demo really fun is we have a DIDCOM mediator that runs in the cloud that is capable of, and we have it configured to accept connections and perform mediation for these parties. And so if I scroll all the way back up to the top of this log here, then we can see what actually happens. The first thing it does is it loads up the code on the page, and then it actually establishes a connection with this mediator, and this other mediator is right now it's hard coded in. You could use any mediator. This is just the one we happen to be using, and so this is the DID that helps it talk to the mediator, and it sends a coordinate mediation mediate request. This is a request from the software running in this page to the mediator. They're saying, hey, I would like you to mediate messages for me, and that's that message. The response comes back. And the mediator says, I grant you mediation. And this is the coordinate mediation protocol that you can find on didcom.org if you'd like to see the documentation for this. And then it provides along with the mediation grant the routing DID that Alice has to use whenever Alice talks to somebody else to make that happen. And so this the routing DID is important because it's used in the creation of a peer did that's actually displayed up here, and the routing information is actually contained inside of it. And so then what happens is Alice sends a recipient update message in the same protocol to the mediator, specifying, hey, I have a new DID that I would like to receive messages for. This is the one that is displayed here and that we also gave to Bob. And the mediator responds and it says, I may have skipped a message here. The mediator responds and it says, yep, I've added it and you're good to go. And then what happens is that Alice connects to the mediator with using WebSockets instead of HTTP, and maintains that WebSocket connection as long as the page is open. And this is the magic to making the message flow really, really fast. And so when it arrives back on our page. And so then, of course, we did the copy and paste of DIDs, and there's other methods that could be used for that, QR codes or discovery using some other method. This is just for the developer demo piece. And then let's get past the status stuff. Here is the first message that was actually sent. What happened was that it created a message and did an HTTP post, in this case, to the endpoint that Bob had arranged, doing the same thing, which is the mediator. That they're actually both using the same mediator, although that's unimportant. They can use separate ones, and the whole thing works. And so Alice does an HTTP post of the message to the endpoint that Bob has provided, and then that mediator knows that Bob has an active WebSocket connection, and so it delivered it live. If Bob didn't have a WebSocket connection, then it would queue that message and wait for Bob to connect. And then it would deliver the message as soon as Bob connected. That's a future feature we're going to add to this demo, where you can take the client into an offline state, so that you can demonstrate the sending of messages and then connecting and receiving those messages asynchronously. Anyway, Bob receives the message, of course, and then the same thing is true in reverse. Bob does an HTTP post to the endpoint provided by Alice, which is Alice's mediator. And then Alice, and then that's delivered live over the WebSocket that Alice is maintaining to the mediator at the moment. So there's two different transports being used, and this nicely solves any firewall issues. So if this Bob tab was running on a totally separate computer on a totally separate network somewhere else in the world, but with internet access, Alice and Bob could still talk the same way, simply by sending to the other party running the Bob tab the DID that Alice has, and vice versa, and then they could send these messages actually back and forth. And we're rendering the messages in a nice way here, but that's the type of thing that can happen. We're only demonstrating basic messages, but of course you can send whatever you want. And this box here that there's nothing in at the moment is designed to be an editor where you can just edit a message, make it say anything that you want, any message type at all, and then send it to the other party as a demonstration, which means you could use this to also not just talk to another demo of the same software, but you use it to talk to any DIDCOM capable endpoint, including a phone or software running on a laptop or whatever else, as an example of how this actually works. So I can't see the chat when I'm sharing. Let me pop back over here. So the mediator DID is not actually acting as the chat room. The mediator DID is only relaying messages into the party that coordinates with the mediator. And so there's not a persistence of a chat room anywhere. The messages only exist between the sender and the receiver. They might be temporarily stored on the mediator, but they're not stored there for any purposes of any of that. What happens if the mediator goes offline? Then the message can't be delivered. DIDCOM allows for listing more than one endpoint to be used, so that you can have some redundancy there, and that's important in high availability systems. But the mediator is designed to be something that you run. This particular one is actually run as a cloud native, not yet open source, but soon to be open source project that runs the mediation services entirely on cloud network providers. So the current instance that you saw was running on AWS. It uses a combination of S3, Lambda, DynamoDB, and a clustered a cluster of what we call SocketDock instances. SocketDock is an open source WebSocket termination software that is already open source, that we've contributed for that. I don't have the GitHub repo for the demo project just yet, but we will soon, and we'll be able to share that around soon, meaning probably not today, because the guy that I was hacking with last night is currently taking a nap, but we'll go ahead and get that up. So I will provide links if you stay current with the DIDCOM group and the other working groups there, then that's where the links will show up when they're ready. Maybe missing something, Martin says, maybe missing something, but if Alice is used as a mediator, how does Bob know this mediator? The mediator is specified in the DID document that Bob resolved for Alice. So inside the DID here that Alice gave to Bob is information about where the mediator is, and that's entirely derived from the DID that's used. Peer DIDs encode all of that information into the DID itself. Other DID methods that have it on a ledger or something else would, of course, record that to the ledger, and then Bob would be able to resolve that and understand that Alice uses a mediator. So Tony, how is the mediator different from what? Tony, if you could finish that question, I would love to follow up on that. A turtle? Okay. From a centralized server. So the difference is that you don't trust the mediator in the way that you would trust a centralized server. So I could post this, for example, to some location, and then it can be picked up, somewhere else. And the centralized server typically, I'll note an exception in a minute. The centralized server typically is aware of the content. It is involved in sort of making sure that maybe it does some filtering for me or whatever else. If you're thinking about it from like a social media site perspective, mediators don't get to see the contents of the encrypted message. It's encrypted all the way to the final recipient, which means that that the mediator is not involved in that conversation, doesn't get to see the content. It's also important to realize that the two people talking don't need to use the same mediator. They do in this example because we only have like one instance of it running, but the message recipient sets up and chooses whatever mediator they want, and then that's the endpoint that Bob transmits it to. Which means that if Bob and Alice chooses her mediator, Bob chooses his mediator, and it does not have to be the same one in order for this to work. So in that case, it's not a centralized server in the sense that that actually each mediator only sees half of the conversation, because they only see the inbound messages for the party that they support instead of seeing messages back and forth at all. It's also possible for Bob to use multiple mediators if Bob wants to. This is an advanced thing that we have that is theoretically supported, but no one's actually done yet. And Bob could request that Alice use different mediators kind of in some sort of random or rotation pattern, so that not any single mediator actually sees all the messages that are arriving to Bob. And so there's a variety of scenarios there that are supported by this architecture. And so hopefully that answers why this is not a centralized server situation. What else can mediators infer about the conversation other than who is conversing? They can inspect the message size. There's discussions of randomly inflating messages to different message sizes. They can also observe somewhat message timing, although that's not a lot. They actually don't see. Well, let's see. So anyone observing traffic to the mediator understands that it's going to the mediator, but not who for, and they understand who's sending the message. Someone who the mediator itself can actually see the recipient of the message, but they don't actually see the sender of the message. They have to see the recipient because they have to know who to give the message to. The sender of the message is actually hidden and only visible to the recipient of the message itself. It's encrypted to the recipient. And so the mediator only knows that they received it from some other party. They have the transmission information, but not necessarily the DID that correlates that. And they know the DID of the recipient because they have to. And so the mediator does see for all messages it's transferring. They can infer things like message sizing, but that's the only thing they can actually see about the messages themselves. So the goal is to not need any trust at all in the mediators. It turns out there is some correlation that can happen simply because of the function of the mediator itself, but there's nothing extra that they can correlate from a meaningful perspective, or that isn't sort of algorithmically understood, that is possible outside that encrypted message. Hopefully I hit all the questions. Did I miss anything important, or any other questions that folks have? We're right up against the time window here. Cool. I would have loved. The only thing that I could imagine that would be amazing would be to have this as a public demo, and you could actually exchange DIDs in the chat and then like talk with each other using this. We didn't quite get there with our hack session to put this demo together, but I'm excited to have this, and we'll definitely make that something that we can pull up, and that way you can play with it. The code will of course be open source, so that you can kind of take a look at how this was done, and the libraries in use and everything else. So this is TypeScript based, this particular example, although it works with lots of languages. Python or whatever, all the Java and stuff. So that's the stuff that's going on. So thanks. I appreciate the invite, Angela. Hopefully this was an informative session. I apologize. I talk fast when I get excited. So those of you watching, if they struggle with that, maybe they can slow down the replay speed of the video. But I very much appreciate it. And hopefully this was a useful and informative session.
Thank you so much, Sam. Yeah, really, really fun, engaging, and it seems like everyone's had a great time in the chat. Yeah, I guess if anyone wants to get in contact with you afterwards, they can contact you through what you shared earlier in the slides. I think I put your Twitter, Sam, in the chat earlier,
Yep.
so people go through that. But yeah, I will end it there because I know we're running over now. But thank you so much again for coming and speaking. Very, very cool. Everyone, yeah, in the chat is giving their thanks. Awesome. So everyone's still here. Hopefully I'll see you in 1 hour where we will have our workshop from Visa. So stay tuned for that. Cool. And without further ado, I'll say goodbye to you now. See you all. Bye.